My name is Colt, and this presentation just give an overview about 10BASE-T1S, which is the newest form of physical layer for Automotive Ethernet, and it's significantly different than other forms of Ethernet that haven't existed. So what's happened in the Ethernet world in general, you'll see a progression from the early days until now, is that speed grade has just been increasing, more speed. In the Automotive Ethernet world, very beginning was 10BASE-T1, which is 100 megabits of bandwidth over a single twisted pair of copper cabling. Shortly after that, there was 1000BASE-T1, which is gigabit. We currently have also multi-gigabit, 2.5, 5, and 10 available, and even above 10 gigabit, 2.5, 5, and 10 gigabit. And now we're there's even pushing beyond that, above 10 gigabit for Automotive Ethernet. But one interesting thing is in the mix of all that, there were some business drivers where the industry wanted to go and have a more cost-effective way of doing Ethernet in a bus topology. We'll see in this presentation that there's some big advantages with multi-drop or bus topology compared to point-to-point. And so that was one of the big limitations of Automotive Ethernet, is that the flavors, except for 10BASE-T1S, all of the flavors are point-to-point to physical layer, which means if you want to connect more than two nodes together, you have to have a switch or a bridge. And that brings in a lot of cost just with the switch or the bridge. And then plus, additionally, we'll see point-to-point networking causes problems with the length of wiring, connections, number of physical layers, PHYs on the network. So the industry took upon itself to attempt to try to create a bus topology for the advantages of the bus topology, and specifically to as an alternative or competition to CAN-FD and FlexRay that's in the market. So everyone knows, anybody that's done any automotive networking knows that CAN-FD's out there and is experienced with CAN-FD. And this particular technology was designed specifically for competition against CAN-FD and FlexRay. So the way that networks exist now in the automotive world, it's really sort of a heterogeneous topology, meaning if you look at a modern vehicle, you'll see that most modern vehicles with a high electrical content do have Automotive Ethernet in them already, maybe 100BASE-T1 or even starting 1000BASE-T1. And additionally, they also have CAN-FD. Almost any modern vehicle has CAN or CAN-FD in it. And if you look at the European OEMs, most of them have FlexRay as well. So we have vehicle topologies, vehicle networks that have a variety of different technologies in them. We call this heterogeneous networks. And in order to bridge data between the different networks, what's required is a gateway. And a gateway is essentially just a hardware with complicated software that bridges data between the networks. And these gateways tend to be very complicated. They tend to have very complex software that often has to be updated, and it causes issues with issues in the field. So the industry, for some of these reasons, wants to drive towards a homogeneous network topology. That means you'll hear the term IP everywhere or Ethernet everywhere. So the drive is to get rid of multiple types of network technologies and just replace it with one type, and that is, of course, Automotive Ethernet. Now, if this can be achieved, one of the big advantages is that we can reduce or eliminate the reliance on gateways. The one advantage of Ethernet is the specifications tell you how to handle addressing and routing, and all that has been baked in over the past 50 years into hardware, switch hardware, for example, automotive Ethernet switch hardware, PHYs, media access controllers. All of these things have been standardized for such a long time that they're all hardware-based. You don't need software to modify the architecture or addressing in routing if you have an Ethernet only, exclusively Ethernet network, because it's well baked into the specifications, which is one of the big advantages of Ethernet. So 10BASE-T1S, 10BASE meaning 10 megabit base T1S, which is a bus or multi-drop topology. 10 megabit was chosen because it was a good, 10 megabit was chosen because most of the network, 80% plus of communication between ECUs in the vehicle, especially for control data, is less than 10 megabits per second. And we see that, for example, where we have CAN-FD, practically speaking, CAN-FD in the field, most OEMs run at 2 megabits or less. So 10 megabit was an achievable speed for a multi-drop type network and covers most of the use cases for the lower end of the spectrum on the bandwidth requirements. So as I mentioned, advantages or motivation, we want to, at least the industry that's involved with the automotive Ethernet, of course, they want to propagate automotive Ethernet everywhere. And there's a drive, as I mentioned, because of addressing the reduction of complexity with multiple networks and other advantages as well. For example, another technology that's available for automotive Ethernet is what's called POODLE, power over data lines. This gives you the ability to not only provide data through 2 wires, but also power to an ECU as well from a source to a destination. So you have the ability for most of automotive Ethernet networks to not only provide data, but also power within given boundaries to different ECUs. And this could be very attractive also from a wiring and reduction in weight standpoint. So the way the 10BASE-T1S works is fundamentally different than all other forms of Ethernet at the physical layer. It does run over single twisted pair copper, unshielded twisted pair copper cabling, very similar to CAN-FD and FlexRay, which is, if you think about the reasons for 10BASE-T1S is to be competitive with CAN-FD, FlexRay. So we want to use the same type of connectors, the same type of cabling, which 10BASE-T1S does. There's a new method for avoiding collisions, physical layer collision avoidance, or in other words, PLCA. This is unique to 10BASE-T1S. We'll get into the details of this in a minute. Bus access method is deterministic. This could be a big advantage over CAN and CAN-FD, whereas CAN and CAN-FD, CAN and CAN-FD have a very unique non-destructive arbitration method where messages are arbitrated, meaning that a message, if there's a message collision on the bus, one message will get priority over the other, and that one message that gets the priority over the other can continue being transmitted without any retransmit, and that's what the non-destructive means, is that there will be an arbitration happening. The winner will be able to transmit without any destruction of the message parts that have been transmitted up until the point where the decision's made who gets the priority. The base frequency that the actual network works on is 12.5 megabaud. We'll explain why that is in a minute. But essentially what happens with any type of bus network, essentially what happens is you have a transmitter, a single transmitter, and a bus network with multi-drops, with multiple receivers. It's only half duplex, meaning you can only have one transmitter at a time. And then while one ECU is transmitting, while one PHY is transmitting, or one ECU or one node is transmitting, all other nodes are in a high impedance mode, and they're just monitoring. They must switch their PHYs to a high impedance, which you see here. There's a stub termination 10 to 30 kilo ohms. So in order to receive, for the network to function, and this is true of every type of multi-dropper bus network, to my knowledge, is you have one transmitter, and then all the other nodes need to switch over to receive mode, and when they switch over to receive mode, they go into a high impedance state. Now, what is unique to Automotive Ethernet, this 10BASE-T1S, is that we do have a capacitive coupled network. So this capacitive coupling that you'll see those 100 nanofarad caps there, that does provide very good isolation. So one of the big features of Ethernet in general is it is either capacitive or inductive coupled, and that capacitive inductive coupling gives you very good, very good DC isolation. With other types of networks, handling flex, where you have to, there is isolation available, but it's not inherently available in the base of the technology. There are isolated CAN transceivers that are available, but you have to actually buy an isolated CAN transceiver. There's isolated and non-isolated. Whereas in Ethernet, if you run an Ethernet, pretty much all forms of automotive Ethernet are capacitive coupled because it's a much smaller footprint on PCB. They're all inherently isolated. So the line encoding on 10BASE-T1S is also very different than anything that we've seen in Ethernet so far. It's a 1 volt peak to peak, 20% margin of error, which is a very big margin of error. But the reason why we can have such a large margin of error is because the data is actually encoded with DME, differential Manchester encoding. Differential Manchester encoding is a very simple encoding method that's been around forever, used in a lot of different communication systems. And it has the characteristic that the data is not encoded based on the voltage level, not based on voltage level, but rather based on transition. So what happens is you have a clock transition every 80 nanoseconds. And then if there is a transition in between the clock transitions, that means that the data is a 1, a bit 1, logical 1. If there's no transition, that means that it's 0. So that's how we transmit 1s and 0s on DME. It's very simple. It also provides some great characteristics, because in DME you always have transitions on the bus. Always there's some transitions that happen, and when the transitions happen, it means that's an opportunity for the receivers to synchronize themselves to the transmitter. So DME gives you a very good inherent ability for the different participants on the network to synchronize their clocks together, which is critically important for any type of network. So most types of automotive Ethernet are very, if you look at what happens, which we've done presentations on this, and we do actually do training on this. But if we look at 100BASE-T1, 1000BASE-T1, multi-gig base T1, first of all, the network's only point-to-point, but because we're doing higher speeds across the same copper wires, there has to be more, let's say, I say DSP acrobatics that happen in order to achieve those speed grades. So there's lots of things like you need a high-speed analog to digital converter. There's something in the PHYs called adaptive equalization, echo cancellation. The recovery of the clock is complex because there's multi-levels in most forms of Ethernet, and then there can be wander of the clocks as well, which all of these things require a lot of complex DSP that happens at real high speed. And in fact, if you look at most of the multi-gig PHYs, or the multi-gig PHYs that are out there, if you run it at 2.5 or 5 gig, or even, and of course 10 gig, you touch the PHY, you'll burn your finger almost, just because of the amount of computation that PHY has to do to send and receive data. So these higher end PHYs at the higher speed grades are very complex inside what happens, and that leads to power consumption and heat heat issues as well. So when we move to 10BASE-T1S, it's a really simple system. All you need is a window comparator, 2-level signals, because we're just looking at transition. And everything else is the clock recovery doesn't matter. DME self-clock, it's balanced. You don't have to, there's no wander correction because there's always transitions happening on the network. And it's a simple 1 and 0. It's just a 2-state network. Whereas the other types of automotive Ethernet might have 3 or 4 different states of the network, different logic levels. Now 10BASE-T1S, as I mentioned, its primary purpose is to be a multi-drop or bus topology so that it can compete with CAN-FD and FlexRay. But it is possible to run it in full duplex, point to point, just like other networks. We should mention that point. Yes, there's a question. Yeah, full duplex is just, if you look at the spec, there's a whole section of the spec. Okay, if you're in full duplex mode, this is how the PHY runs. If you're not in full duplex mode, this is how the PHY runs. So it's a whole set of the physical layer works differently if you're point to point full duplex compared to half duplex. Now the details of that I'm not prepared to talk about, but it's a totally different way in which it runs. It's still DME, but in order to get the data both directions at the same time, fundamentally things have to change.
Yeah, you have to look at.
Right. It would be acting more like a point, but there is a mode. It is supported by most PHYs for point to point for 10BASE-T1S. So another question.
How's the IP address resolved when you have one?
Oh, okay. IP addresses, it's interesting because you might think there's a problem with this IP address. First of all, when you say IP address, that's a logical address, an Internet Protocol address. IP only applies to IP, TCP/IP, and UDP/IP, for example. If we look at what the physical layer of the network itself, the lowest level type of addressing is the MAC address, the physical address, not the IP. And that's every single message. But in this case, you might think that having a bus topology would be in conflict with the addressing, but it's not. Essentially, all the nodes on a 10BASE-T1S network, they must have their own MAC address, own unique MAC address, just like every other Ethernet node. There's no difference. They can optionally also have their own unique IP address if IP is used on a network. But remember, IP is it's optional. It's not required. MAC address, physical addressing is required. Every node will have its own MAC address. The only difference between the standard Ethernet and this newer form of Ethernet that's a bus topology is that when a transmitter transmits something on the network, all receivers will receive that. And then so the receiver receives a message and it can inspect what is the destination MAC address. Is this for me? Yes, I'll consume it. Is it not for me? Then I'll just ignore it. So the decisions about what happens to the individual frames would then happen in the media access controller, the MAC of the individual nodes.
But they're all connected to the same.
They're all connected to the same network, the same 2 wires, and they'll all receive the messages at the PHY level. They'll all still receive the messages, even if it's the wrong MAC address. But the media access controller then will say, hey, this is not my address. Just toss the message. That makes sense?
Does that also put any special requirements in the switch itself, or regular switch?
The only requirement on the switch, so switch technology is at layer 2. It's a MAC layer and above. So the 10BASE-T1S, the only requirement on the switch, if you want to connect a 10BASE-T1S network to a switch, the only requirement is that the switch port that this network is connected to, the switch port, has to have a 10BASE-T1S transceiver or a PHY, a 10BASE-T1S PHY. Does that make sense? 10BASE-T1S is not compatible with any other automotive Ethernet network. Therefore, if you want to hook this to a switch, you can, but you just have to have the right PHY for that, 10BASE-T1S PHY. So instead of, for example, instead of node 0 there on this picture, that could be a port of a switch, node 0, could be. And it works fine. Because you can have a single port of a switch with multiple MAC addresses connected to it. You can have that, that works fine. So this is just like the scenario where you have multiple MAC addresses connected to a single port of a single switch. It's identical, it's no different. So switches for 10BASE-T1S do not have to change at all, none, except with the restraint that if you want to connect the 10BASE-T1S network to a switch port, that switch port PHY, the physical layer, the PHY has to be 10BASE-T1S naturally. Because 10BASE-T1S is not compatible with any other form of Ethernet. Good question. Okay, so the reason why I mentioned, I'll tell you the reason why the network, it's a 10 megabit data throughput network, 10 megabit, 10BASE-T1S, 10 megabit data throughput network, but the network runs at 12.5 megabytes. Why the extra, bandwidth? The reason why we need the extra bandwidth is because the data that's transmitted on the network, there's some overhead that has to happen in order to manage the different nodes and manage traffic and get the network up and running correctly. So we have to, the PHYs have to exchange data that is not let me back up and say, the PHYs have to exchange information that is not related to the data that you want to transmit in order to run the network. And so what happens is there's a 4B to 5B, 4 bits of data that you want to transmit gets converted to 5 bits of data on the network. And that extra bit, you'll see here in this table, 0 through F, that's your 0 through 16 hexadecimal, 4 bits, right? And then after that, IJ, the numbers I, J, K, T, and so forth, the extra bits, the extra ones, are special symbols that are used to enable the PHYs to communicate to each other and cause the network to function. They're very special things that we'll talk about some of these in some of the future slides of this presentation. But when you go to transmit 4 bits on the network, that gets translated into 5 bits that actually get transmitted on the electrical wires. So the way it works is essentially you have an MII interface, media independent interface. This is sort of standard for all Ethernet interfaces. On the left-hand side, you would have a media access controller. So you got a media access controller, either a port of a switch or in a node. And then that dotted line then would be into the PHY from an MII interface. You get a scrambler. This is from some standard, the scrambler is a pretty standard technique to scramble data so that it pushes the power band out or stretches the power band out and reduces the peaks. By doing scrambling, it just is sort of randomizing the ones and zeros that happen on the network. And by doing that, you take the peaks of the power band at certain frequencies and you can drop them down and essentially stretch the power band out over a wider frequency range, and thereby reducing the peak of the power band, thereby reducing your electromagnetic, what you transmit from electromagnetic standpoint. So disturbance on EMC. So scrambler happens, and you do a 4 to 5B conversion. Then the special symbols are inserted inside the PHY. And you get a serializer, then a DME encoder. Data goes out in the network, and on the receiving side, it's pretty simple as well. Deserializer, remove the symbols, do the 5B to 4B conversion, descramble, and the data comes back. What is different about 10BASE-T1S is that because it's a bus network, it's possible that the MAC the MAC that's attached to this, it's possible that the MAC wants to transmit something, like the node wants to transmit, but the bus is not available because someone else is transmitting. So this is a unique scenario for modern Ethernet. Modern Ethernet, anything in the last 20 years, you have full bandwidth in both directions. That means, I don't care what node you are, you can transmit anytime you want, and you're going to get a full bandwidth network available to transmit at any time you want. So that's different than 10BASE-T1S. Now we got multiple transmitters on the same two wires. You cannot transmit at the same time on the same two wires. So, so what happens is that 10BASE-T1S actually uses a very old technique, the CDS-CMA, the CDS carrier sense collision detection is actually there's some legacy legacy pins on an MII interface, collision detection and carrier sense, that are actually used for 10BASE-T1S. And this will tell the MAC, the media access controller, wait a minute, I can't take data right now, basically. And by reusing these old concepts, the carrier sense and the collision detect, these go back to the 70s, it enables the PHY to be lower cost, because the only other way to achieve 10BASE-T1S on a multi-drop network where only one node can transmit, that means some nodes will have to wait. And some nodes have to wait means you'd have to buffer the data, right? So instead of buffering the data in the PHY, you could specify and say, okay, in the PHY, you have to have a certain amount of buffer to handle this possibility of collision, but then that increases the cost of the PHY. Then you have to have memory in the PHY, and it adds a lot more complexity. And one of the main intents of this is to be very low cost, very simple type of network, as simple as possible. And essentially, what 10BASE-T1S has done is push the logic for the case where there's the network is busy, is like a collision detect in the old world. So it is interesting because we've had media access controllers out on the world for probably since the 90s, 80s really, since the 80s. So that's about 30 years, and none of them have ever used collision detector carrier sense. But it's still in the specification. So now, because of 10BASE-T1S, we're finding ourselves, even at Intrepid, we have to be a little careful with the MAC, the media access controllers that we use, the fact that we have to actually test and make sure that they work with COL and CRS, because those have been unused for the last 30 years. So that would be one thing to be careful of with 10BASE-T1S. There are some Macs out there, Mac controllers, that, you know, the collision detect has gone by the way of the dodo. It's kind of, you know, no one's tested it in 30 years because it's not been used. But 10BASE-T1S is bringing that back. Okay, just by way of comparison, looks like I have time to do this. Methods for handling collisions. I like to do this slide because different networks out there handle things in different ways. In LIN, it's called LIN, Local Interconnect Network. Like anytime you have a network, there has to be a way of managing collisions or making sure that collisions don't exist on the network, so that a transmitter can get its data through to the receivers. In local interconnect network, you have one master node that says, okay, you transmit now, so master-slave type of network topology. The master tells everyone when they can or cannot transmit. FlexRay has a TDMA, time-divided media access. This just means you're splitting up the network into time divisions. So you got node A can transmit now, node B, node C, node, and so forth. And that cycle continues. That's TDMA. TDMA is fundamentally how wireless networks work also, is because If you have multiple nodes on a wireless network, you just have one medium. It breaks up the time which each node can transmit, but based on time slot. And that's the way, it's a common way of doing collision avoidance, and FlexRay is TDMA. CAN is non-destructive arbitration. I described that already, where if two nodes or more nodes want to transmit on a network, the arbitration ID decides which one makes it out on the network non-destructively. The lower the number, the higher the priority. So 0 and CAN is the highest priority message. 100BASE-T1, 1000BASE-T1, multi-gig T1, and all other forms of modern Ethernet, including what's in this building, use point-to-point physical layer only, full duplex. What that means is that you always have the bus 100% available. Every transmitter has the bus 100% available 100% of the time. So it means that there's just really no possibility for collisions. And now with 10BASE-T1S, we have a brand new method called PLCA. You'll see that PLCA, it looks something like TDMA, but it's not exactly TDMA, and I'll try to explain that in a minute. But the way 10BASE-T1S works is you have, I shouldn't use this, I have the words in here, master and slave. The industry is going away from that. It's coordinator and follower, so I'll try to use those words, but coordinator and follower to get rid of the political incorrectness of master and slave. But so ECU 0, whichever, in a PLCA network, 10BASE-T1S, every node gets a number starting with 0. 0 through how many ever nodes there are. And 0 automatically gets the job of being the coordinator, the master. All that means, though, it doesn't do a lot. All that means is that that coordinator or master sends out a beacon. It's a special symbol. A beacon's one of those 5B special symbols. Remember I said in the table? The special symbol is not data that you're trying to transmit, but it is information that the PHYs need to communicate to each other. One of those is a beacon. Beacon's a special number. It goes out on the network, and all other nodes receive that beacon, and they know, okay, now we're starting a cycle, starting a special PLCA cycle. Then at that point, the node 0, each node starting with 0, then 1, then 2, will have an opportunity to transmit. Now, it's important to understand, I say opportunity to transmit. It means they don't have to transmit. It's just an opportunity to transmit. If the node wants to transmit, it'll send a special signal, a special symbol on the network saying, yes, I want to transmit. And then it'll transmit an Ethernet frame, standard Ethernet frame. If it doesn't want to transmit, it just does nothing unless a timeout is declared. So the reason why PLCA is not strictly TDMA, why it's not time divided, is because each node has an opportunity to transmit. If it transmits, then it uses how much ever time it takes to transmit the frame, up to 1500 bytes. If the node does not transmit in its opportunity, then it just lets the opportunity expire, and that's a short amount of time. So these slots grow in strength based on if you're transmitting it or not. You have a question up there?
Now, your network has to be statically configured.
Yeah, correct. Yeah, so the question, the comment is now the network has to be sort of statically configured. There are a couple comments about that. Short answer is the current version of 10BASE-T1S has to be statically configured. You have to configure every node to know which is node 0, which one's 1, which one's 2. If you add a node, you have to reconfigure all the other nodes. This is kind of reminiscent of what makes FlexRay difficult. Exactly, and that's true. And so that's one of the disadvantages of 10BASE-T1S in its current incarnation, in its current form, similar to FlexRay. However, there is work happening. John Simon mentioned it in his last presentation. It's not available yet, but soon there'll be a spec called topology discovery. And that is 10BASE-T1S PHYs will have the ability in the future to discover for themselves how the network's configured, and you don't need to do that in software.
That's still required when it goes through.
No matter what, it works the same. Once everything's configured, it'll work the same. There'll still be a node 0, there'll still be a coordinator node, but what the topology discovery does is on boot, it says, okay, how many nodes are out there? Who's going to be node 0? Who's going to be node 1? Blah, blah, blah. There's a whole, negotiation that happens on boot up. In that case, you don't have to statically configure anything, right? So that's one of the advantages currently with CAN, CAN-FD, CAN-XL. You'll hear those guys saying, hey, no, we got non-destructive arbitration, just remove nodes, add nodes that you want, and it just works. And that's been one of the big advantages of CAN, is you don't have to program a single node to know anything about any other node. It can be totally independent. Yeah, in CAN, it's just bad. The only bad thing you got to avoid is don't send the same ARB ID as some other node. That's pretty much all you have to worry about. But in 10BASE-T1S, you have to configure all the nodes to understand how many other nodes are on the network and node IDs and things like that currently. But there is coming topology discovery to eliminate this limitation or disadvantage relative to CAN-FD.
Does this impact the upper layer, the software, or?
Okay, really, really important. This is a good question. Does this affect the upper layers of the software? Ethernet, answer is no. None. Zero, not zero. I don't know how to emphasize it more than that. It does not impact one thing about upper layers. This is designed as an Ethernet only network, meaning it's a new type of physical layer. But just like with every other type of Ethernet, once you hit level 2, once you hit the MAC, the media access controller, there's nothing different whatsoever. So media access controllers don't change. You just have to check that they support the carrier sense and collision detection. But that's been in the standard since the since the standard existed in 1981 or 82. Just the media access controller has to support the carrier sense and collision detect, which has been in the spec. That's the only requirement. And above that, the hardware and the software will not even know it's a 10BASE-T1S network. They won't even recognize it as there's no difference. You don't know you're even connected to a 10BASE-T1S network as compared or 100BASE-T1 or 1000BASE-T1 for that matter. It's identical. The Ethernet frame's identical once it hits the MAC controller. It's really important to understand that. That's the big advantage of the 10BASE-T1S. So let's go through some examples of how this works. Let's consider a 4-node network, nodes 0 through 3. If no nodes are transmitting, that's the minimum PLCA cycle. That's essentially just a beacon goes out. Node 0 says, I don't have anything to transmit. Node 1, I don't have anything to transmit. Node 2 and 3, the same. That just means that the transmit opportunity window, which is 20 bits, expires every time. That's the fastest cycle. The next one, let's just say nodes 1 and nodes 3 have something to transmit during this cycle. And so then node 0 lets its transmit opportunity expire, 20 bits. Then node 1 says, hey, I want to transmit. So if a node has data that it wants to transmit, it's required to send a special symbol, a different special symbol, a 5B symbol on the network called a commit. It's just a special number, that's all it is. Special number, special 5-bit number that tells all other nodes, I'm ready to transmit. And all other nodes have to go into IEPs, they synchronize their clocks, the transmitter, you're ready to receive data. Then node 1 will transmit up to 1500 bytes. That's a standard MAC frame. Standard Ethernet MAC frame. MAC address, destination MAC address, source MAC address, ether type, blah, blah, blah. Data. Minimum 64 bytes, maximum 1500 bytes, standard frame. Then after that's done, there's another special symbol that says I'm done transmitting, which I don't have in the slide. And then node 2 has a transmit opportunity. It expires. Node 3, hey, I have data. Same thing happens. Sends a commit. The data it wants to send, and then after node 3, the cycle expires, and then you get another beacon. And then if all nodes are transmitting, it's pretty simple. It looks like right here I forgot a commit. I need to add that. This is wrong. You get a beacon, and then you get a commit, and you get data, commit data for all the nodes. And again, I don't represent it here, but at the end of the transmit, there's also a special symbol that goes out and say, hey, I'm done transmitting. But the data there is essentially a standard macro. Yes.
At the end of the frame or at the end of the module, so it comes out. Or each node.
At the end of each packet, Ethernet packet, there is so what I'm showing when I'm trying to I'm trying to prepare for there's some special features that I'm talking about in just a second. So I don't want to. So in this scenario, what I'm showing right here is every node is just transmitting one packet within its transmit opportunity, one message. Now that one Ethernet packet, that one Ethernet frame, that one Ethernet message that's being transmitted will be followed by a special pair of symbols that say, hey, I'm done transmitting. And then all other nodes then can do their CRC checks and make sure that they receive the data correctly. However, there's another feature that I'll talk about in a second where nodes can transmit more than one frame per transmit opportunity. That's called burst mode. That's another slide. So that works a little bit different. But in this case, I'm just representing one node transmitting one packet, one Ethernet packet per transmit opportunity. So burst mode, as I mentioned, is right here. So in non-burst mode, this is what I was trying to say. You get a commit, data, and then right at the end, there's two special symbols, ESD followed by ESD OK. This just means that, okay, I'm done. But it's important that to understand that there is a feature called burst mode that enables one or more nodes to transmit up to 255 Ethernet packets per transmit opportunity. Now, the reason why this is important is because with almost all networks, if you look at almost all networks, there are going to be a small number, sometimes just one node that is a large producer of the data on the network. And other nodes, most of them, in most cases, are more consumers of the data. They don't produce much data. So there's always this asymmetric nature to networking in automotive that I've seen where, in the powertrain network, the powertrain ECU naturally is going to produce most of the data on the network. So often you have a small number or a single node that produces, a large majority of the data that's on the network. So if burst mode didn't exist, then it would be difficult for that node that produces a lot of data. It wouldn't be an efficient use of the network. You would have to, if the nodes that produce a lot of data would not be able to get enough bandwidth reservation for that entire network to run the network efficiently. So this burst mode allows you to configure the network to run efficiently based on who are more producers of data, who are more receivers of data. I do remember it's configurable. The transmit opportunity and number of bits is configurable. 32 is the default. Yeah, but it is configurable. The beacon is not configurable. When I said the Ethernet frame is identical, I kind of lied a little bit. 10BASE-T1S does have a little bit of a unique frame structure, different than other Ethernet on layer 2. It doesn't matter because the PHY strips this out. You won't see this on the Mac side. if you took a scope and you measured the two wires, you're going to see this. But if you looked on the MII side, if you looked on the Mac side, you're not going to see this. You're going to see a standard Ethernet frame. The physical layer does a translation. So what happens is that to avoid using additional bandwidth, we put some of the special symbols that are needed, like the commit, in the header of the Ethernet frame itself. That's all that this is. So in an Ethernet frame, a standard Ethernet frame, you have a preamble that's 7 bytes, and then you have a starter frame delimiter that's additional bytes. So it's 8 bytes of a special header of Ethernet. This is the standard header. So what 10BASE-T1S does is it replaces that standard information with first the commit symbol. That's the JJHH. And then there's a scrambler in the PHY, as I mentioned before. The scrambler stretches out the power band. There's a descrambler initialization, and then finally you get a preamble sequence as if the 5555B is the 101010 pattern from the standard frame. So the commit and the descrambler information is new information that's shoved into the header of a Ethernet frame. It makes it a non-standard frame, but nobody cares anyways, because the only thing that a 10BASE-T1S5 can connect to is another 10BASE-T1S5. That can't connect to anything else. Yes.
Should the preamble come before the commit? Because you want the receiver to synchronize to the preamble signal.
I don't know the answer to it off the top of my head, but this is how it is in the spec. Like the synchronization, I will say there is an opportunity for the PHYs to synchronize just with the beacon itself. Because the beacon symbol that comes before this, at the start of the cycle, all receivers will synchronize by default to node 0, because node 0 is the one that has it's the only one that has even the opportunity to transmit. Another question? It's known, correct, yes. Mm-hmm. That's true. Descrambler? Right. Yeah. Correct. Yeah. So the transmitter sends the descrambler initialization to all of the receivers, and that's where that data gets. The entire sequence, I don't know from the top of my memory what happens there, but that's a good question. Right. So I'm assuming that at the point of commit and this descrambler initialization, descrambling, based on this, I would say descrambling only happens in the data section, after the data section. Okay, so we're running out of time. Now, 10BASE-T1S, as I mentioned several times, is designed to be competitive with CAN-FD, and I'm going to show you why, in order to achieve that, why we have to have a bus architecture. I'm going to show that, but before that, one of the other limitations with Ethernet compared to CAN-FD and CAN is that Ethernet up until 10BASE-T1S requires an MII interface. There's many different MII standards out there, but the one with the minimum number of pins is 10 pins. Which 10 pins for silicon on a PHY is very expensive from a real estate standpoint on a PCB. And CAN, controller area network transceiver, CAN transceiver, has only, you can get CAN transceivers with like 3 pins, 3 or 4, 5 pins, with including power. So Ethernet in that way has not been competitive with CAN because of just the pin count, real estate size of the chip standpoint. Therefore, to overcome this, there are available and will be available several ways of overcoming this. Now, the MII has always been the boundary between the MAC and whatever physical layer that you have. So that's the boundary between layer 1 and layer 2. It's always been the MII. So we got to kind of massage that boundary a little bit to overcome this problem. So in the upper left-hand corner is your standard MII interface, which is minimum 10 pins, where you have PLCA, 10BASE-T1S PHY. There is a possibility that you can have a SoC, for example, and just have an integrated PHY. To look at the one below this. Integrated PHY is where you just have one chip. It's got the analog part built in. It's got PLC built in, a MAC built in, and then also microcontroller or FPGA, whatever. That's a possibility for companies that want to integrate everything into one chip. Then we have the possibility of having also a MAC PHY. And MAC PHY is where essentially you're going the other direction. You're taking the MAC and you're putting it into PHY. So you got a MAC and a PHY in one chip. And what that does is that means the other side of the MAC can be whatever interface you want. And then Open Alliance has specified a 5-pin SPI interface, so like a standardized SPI interface to come out of a MAC PHY chip. So this, you're putting the MAC in the PHY. And then down below in the lower right-hand corner, we have what is normally standard with CAN, and that is you have the logic, the digital logic, including the PLCA and the MAC in one chip or in a microcontroller, and you separate the analog part out. And so that's a transceiver then. Then you get essentially a 10BASE-T1S transceiver. It's just the analog part. And then the interface between the PLCA and 10BASE-T1S analog part is just 3 pins. So there are some manufacturers coming out with a transceiver PHY, just the analog part, and our MII is out now. As time goes on, we expect that there'll be some integrated PHYs and MAC PHYs available as well. Okay, last slide. So this is a slide that shows you why you need a bus topology to be competitive for low-cost networking. This is the reason. In the upper left, we have standard Ethernet, point-to-point Ethernet. Point-to-point Ethernet means that one ECU or node can connect to only one other ECU or node or physical layer. So let's just say that we want to have a 5-node network, which is what all of these pictures are 5-node networks. You have sort of like this main node ECU at the top, and then you have unit 1 through unit 4, which are also ECUs. So if we want to connect these together with standard Ethernet, point-to-point Ethernet, means you just have, first of all, you have to have a switch in the ECU, and then each part of the switch goes to one ECU. So if you count how many PHYs do I need to do this? How many PHYs do you need to do this with 100 base or 1000 base T1? It's 8. With CAN-FD or with 10BASE-T1S, because it's a bus network, because it's multi-drop, count the number of PHYs on that picture, and you're going to see it's 5, both CAN-FD and 10BASE-T1S. So it reduces, a bus topology gives you the ability to reduce the number of PHYs that you have compared to the PHY to ECU ratio is smaller compared to a point-to-point network. And then that just propagates through as well with connectors, cabling, and so forth. It's a lower cost network from all of that standpoint. So you see number of connectors on the point-to-point network is 4. 10BASE-T1S CAN-FD is 1. Cabling, you have 4 separate cables and 10BASE on a T1 network. T1S or CAN-FD is just 1. The big benefit of the point-to-point is that you go much higher in bandwidth, much higher in bandwidth, up to currently 10 gig. Whereas in both 10BASE-T1S and CAN-FD, you're limited to under 10 megabits per second. So hopefully this represents the reason why we need bus networks in automotive from a cost and connector PHY standpoint. These aren't going to go away. Yeah, question.
Just really quick, you could have a 10BASE-T1S go to ECU without a switch, hopefully, right?
Yes, correct. So in this picture, I have ECU at the top with a switch. Now, the only reason you need a switch is if you have another Ethernet network connected. Now, if you remove that 100,000 base T1 network, then you don't need a switch. You can just bring that right in as a PHY, and then you just need a MAC somewhere, a media access controller, and then you get all the data from all the networks. Correct.